right, so we are on the section on circles, and one of the things that we're doing here is we're finding out different parts of the circles. If you notice here, this is the circle in front of CVTC, and I show that the diameter, the distance across, is almost 40 feet. Sometimes we're confused that something looks like a circle or part of a circle when in fact it's not. This is too wide at the bottom to be a real circle. When I measured the circle in the front of CVTC, I found it to be 40 feet 6 inches instead of just under 40 feet. But that could be because I couldn't get the screwdriver into the ground on the other side because the ground was frozen. This also is not a circle, and it's probably easier to see that it's not a circle because it's much more spread out. Here I show not just the diameter of the circle, but also the radius. Google Earth has a fine program that shows you the math of all of those things. Let's see if we can figure out the math of a circle, much like they did the math here. Well, we know that the radius is half the diameter, so 19.74 times 2, and we do get that almost 40 feet. The area is the radius, 19.74 squared times pi. And when we multiply that out, we do get what did I do wrong here? Oh, that's in square yards. All right, so we have to take this, that's how many square feet it is, divide that by 9 because there are 9 square feet in a square yard. A square yard is 3 feet by 3 feet, or 9 square feet. And we get 136 is the area. Their circumference is pi times the radius times 2. And when we do the math there, oops, let's see where I made my mistake. Times, delete, shift pi, and we get 124.02.03. So you see how those calculations are made. Here is the light over by CVTC, and that shows the diameter is 8 inches, so the radius would be 4 inches. And then we can figure it out. One of the things that people want to know is how many digits to pi they can get. It would require 39 digits of pi in order to compute the circumference of a circle of the radius that is as far as you could go in 20 billion years at the speed of light. So that the upper bound, that would be the radius of the universe. And if you had 39 digits of pi, you would be off by less than the diameter of the radius, less than the radius of a hydrogen atom. So you do not need to calculate very many digits of pi. 39 would be way too many. Here we show another circle. This is a bird bath in my backyard. Here's a semicircle. The semicircle starts here and it completes its route there. This is a circle in Washington, D.C. I was kind of confused at first because it's a fountain. It's a fountain, and if you notice, you can see the shadow of the water on the fountain. I'm not sure where exactly in D.C. this is. I don't think I've ever seen it. Here's the Washington Monument, and it shows kind of an ellipse shape on each side, but then right here at the very center is indeed a circular drive. North of the White House is a semicircle, and the south lawn has a kind of an ellipse in it. Well, you know what? This might not even be a semicircle. It might be a parabola. I'm not sure. Yeah, it's not really circular, is it? The fountain is definitely circular in the front yard. This table, you can see at CVTC, has a diameter of 30, what is that? 33, 34, 35, 37 inches. So if we took, if we took 37 times pi, we would get 116 inches is the circumference of that table. Here I show one of the planters out in front of CVTC, and you can't see the radius, but we know the circumference is 12 feet 7 inches. So if we took, let's get our calculator out, if we took 12 feet 7 inches, oops, there it is, 12 feet, oops, clear. Let's do it this way. 12 and 7/12 feet. And then multiplied that, I'm sorry, that's the circumference, so we need to divide that by pi. We get 4 feet is the diameter, and I think I show you that it is a little bit more than 4 feet, 4 feet a half an inch. Here's another one where we see that the circumference of this concrete pillar that holds the lights up is 4 feet 9 inches. Well, 4 feet 9 inches is 57 inches. So if we take 57 and divide it by pi, we get 18 inches is the diameter of the concrete here, which kind of makes sense because that's how big those pillars are. This is kind of interesting. This is that same pillar, and if you notice, the tri-square or the carpenter square here is tangent. We're going to learn about tangent in just a few seconds. Tangent to the circle over here at 9 and tangent over here at 9. And so in fact, these two tangent spots mark the endpoints of the radius, and so it forms a square. The other parts of the square are inside the pillar. Here's another one where you can see the radius of this light pole is 4 inches. Let's do the math though, because it says the circumference is 25.5 inches. So if we take that 25.5 and divide that by pi, we get 8 inches is the diameter, or the radius is 4 inches. Here's a post inside the lunchroom at CVTC, and if you notice, it's 9 inches in each of these tangents, and so the radius is 9 inches, which means the diameter is 18 inches. And once again, we have 4 feet 9 inches, which we just did before, didn't we? Didn't we do 57 inches divided by pi? Thought we did. Yeah. And we got 18 inches was the radius. Down below that pillar is another pillar, or the inside of that pillar, and that has a radius of 8 inches. And if we look at the if we look at the circumference, we get 4 feet 2.5 inches, which would be 50.5 inches. So we can take our 50.5 and divide it by pi, and we get 16 inches, which is the diameter, since the radius is 8 inches. This is the flagpole in front of the Gateway campus, and what's interesting about it, or maybe it's the main campus, now I can't remember, is that the bottom of it, it looks to have a radius of 5 inches, and then as you go higher and higher, it gets skinnier and skinnier. At this point, which is a little bit above the bottom, it's 2 feet 8 inches, which is 32 inches. So if we take 32 divided by pi, we get 10 inches, and so it's, I guess that's about what it was at the beginning, wasn't it? So it hasn't shrunk too much that high up. This is one of those lights in front of the main campus, and it looks to be about 4 3/4 inches. So if we look here, if we look at the circumference and we find it to be 28 inches, 28 divided by pi is 8.9, or about 9 inches, which would make it about 4.5 inches as the radius. Here's an interesting one. Here's a circle that has a radius of 1,318 feet, and the area, which is pi times radius squared. You can see that there's a sector here of the circle, a pie-shaped piece of the circle that is cut out. Now we can find out what that pie-shaped piece is. This, by the way, is called the arc of the sector from here to here. We can find what that area is and figure out what the area of the circle is if we know what this angle here is, and the angle appears to be about 70 degrees. So math-wise, we would have a proportion that looks something like this. Our circle has an area of 603,723, and that's for 360 degrees, because that's how many degrees there are in a circle. We want to know what that would be if we would find the area of the circle. Let's use the letter X for the area of the circle. The letter X over, and I said that looks to be about 70 degrees. And then we're going to solve that for X, and we get 117,000 feet, or about a sixth of the circle, a little bit more than a sixth of the circle. Here's an interesting thing. This is an inscribed angle in a circle. If the vertex of the angle touches the circle, then it's an inscribed angle. Here we see some circles that have tangents to them. Every place where the road here touches the circle, you can see that there's a tangent to the circle. I'm not sure if there's a road here or not. It's hard to say. Here it looks like there's a road just up to the center. Here's a road for sure on this part up here. There can be no tangents to joint circles if inside this area. For example, if we had a tangent between these two, it would go straight through the center of this circle. The only way that it works is that we have tangents along the bottom here, and so it depends on what shape the circle, or what arrangement the circles have in order to draw a tangent. Here's a chord of a circle. It goes from one side of the circle to the other side, and if you notice, they have a different crop that they're growing in this section, and the I guess it doesn't show what the area of that is. It just shows the length and the width. Excuse me. Oh. Here's another chord. This chord of the tire goes from 1 inch, about a half an inch, up to 5.5 inches, or about 5 inches. So if you could imagine this tire being a circle, it's got a chord off the one side that's 5 inches wide. The tire itself looks to be about 5 inches wide, the part that's touching the ground, I mean. The diameter to the cord looks to be about 27.5 inches. The diameter across the tire, instead of being 27.5, is actually 27 7/8. Well, if you take the area of the bottom of the circle, as I said before, it's 5 inches by 5 inches. If you take that area and multiply 5 times 5 is 25. Multiply that by how many pounds there are in each square inch. Since there's 25 square inches in the tire, times 35 square inches, times 4 tires, you get 3,500 pounds. I looked up what the weight on a CRV is, which is what that tire was, and it's around 3,300 to 3,500 pounds. So as I said before, we had 27 and now let's do the math here. I'd put it in here someplace. It was square root Yeah, 27.5 minus 2.5, and multiply that by 2, you get 27.422, and I said 27 1/8, but it probably was closer to 27.5. All right, so here is another spot where we have the polygon, and we found the area of this part of the field is 180,000 square yards. Here's a circle that has a radius of 1,344 feet, and this chord measures 2,477 feet. So what we've got here, we could figure out what the area of that sector is, because we could figure out what the area of this part of the circle is, and then subtract the area of this triangle, since we know the size of the triangle, and that would give us the area of the light tan section of the field. Here's a diagram that is from your book, and it shows 2 tangents to the circle, and if you notice, it's actually tangent to each of these circles along the way. And we can find out what those tangents, that the length of each of those tangents is the same. I drew the 2 tangents, and they are 18,492 feet. This is probably the most fun that I've had in this lesson, is the intersecting chords theorem. Here we see a chord that is 18 long, and here we have a chord that is 17 long. This first chord is split into 2 sections. Let's see, 5. This top one is 5. This section of the chord is 5, and this section is 12, because 5 and 12 makes 17. 5 times 12 is 60. Well, we can do the same thing with the other chord. We see that it is divided into 2 sections. One 12 long from 18 back to, no, let's see here. What am I doing wrong? I'm sorry, this is 16, not 18. From 16 back to 6, that's 10, and the other one is 0 to 5. So what we've got here, so this section is 5, and this section is 12. This section is 10, and this section is 6. 5 times 10, or 12, excuse me, equals 6 times 10. So that's the math that you can see is done in this problem. And that's what you can do with the intersecting chords theorem. Let's look at some more of those. Oops. Here's another one. Yeah, I showed that one over again. Here's one that is broken up into two spots. This one is 2, and this one over here is 15. This section here is 5, and this section here is 6. 5 times 6 equals 2 times 15. You know, I was thinking you could make a calculator out of a circle and 2 rulers. That'd be pretty fun to do. Like I said, I just thought that was pretty interesting stuff. Here's another math example that you can see. We found the length of this full chord to be 1,409 feet. This section is 1,175 feet, so we could figure out how long the other section of that circle is. And the total radius is given there too. Here's the most fun use of the inscribed angle, and that is the theorem that says an angle inscribed in a semicircle is a right angle. So in other words, from here to here is the diameter. But more importantly, it's also, if you notice here, we can figure out what the what that circle is by just taking these measurements from here, 0 up to, what is that, 20 1/4, and 0 up to 16. So on our calculator, we can find the square root of 16 squared plus, what was that, 20 3/8. 20 3/8, and we get, oh, I forgot to square it, sorry. Squared equals 25, almost 26 inches. So I have a hunch this manhole is 26 inches across. There's some more math that we have in this problem. One of them is, if you notice, the bridge is actually a circle on top of a rectangle. The distance all the way across is 135 3/8 inches, and this steel is actually, aluminum is actually 6 inches wide. So if the total height is 142.5 inches, we could figure out how wide, how tall a 10-foot wide object could be and still go through the tunnel. Well, here we see the math of it. This is 42, let's start at the beginning. This is 135 3/8 inches across. So if we subtract 2 6-inch pieces, one on this side and one on this side, we're down to 124 inch. Where did I do that math? 120 inches. I'm sorry. No, it'd be 124 inches. The height is 142.5 inches. Subtract 6 inches is 136.5. Oh, I'm sorry, here it is. It's 123 5/8 inches is the distance inside the steel. Divide that by 2. The radius here is 61 13/16 inches. So since the distance all the way to the top is 142.5 or 136.5, subtract that 61 13/16 means that the bottom part here is 74 11/16. Well, if this distance from here to here is 61 13/16, and this distance from here up to here, we know we can figure out how tall the object can be and still fit through there. We could also figure out in this case that you can go, if you wanted to be at 10 feet, you could have something that's 7 feet wide here and still be able to go through if it's 10 feet tall. Here's the math that shows the 42 inches. One of the problems that you have to do is do a pulley around 3 circles. I thought it would be kind of neat to do a road that goes around each of these circles, but then it's tangent at the ends. Here's a garage door that's kind of like one of the problems that you have in the book. And I did the math on the garage door. I know it's 8 feet across and it's 9 inches high here. So if I do the math, I would take 42 inches squared. That is this side of the triangle. This side of the triangle is the radius. Subtract the 9 inches that is between the end of the curve and the height of the curve. So the radius minus 9 inches, and then each of these on the ends would be the radius. So I can do the math and I get 42 squared plus r minus 9 squared is r squared. I take r squared away from both sides and I get 42 squared minus 18r plus 81 equals 0, or the radius is 42 squared plus 81 divided by 18, or the radius is 102.5 feet, which is a little bit less than 9 feet. That's the lesson.